All right, welcome to another class in EGR 321 or EGR/PHY 321 Engineering Dynamics. What we're going to be covering today, we're going to be starting on chapter 16. Some brief announcements, kind of like as we're going. CLO 9 assessment is going to be due on Monday, the April 6th. Okay, that's going to be through 8 a.m. and 5 p.m. You must complete this before the time ends, so make sure to get everything set up, and then also upload your work to D2L Dropbox. This is going to be covering sections, the last sections of Chapter 15, right? So it's 15.6 and 15.7. The homework for CLO 9, which is over those same sections, are going to be due this Friday at 5 p.m. I just want to make a brief reminder that when you're working when you're going through these videos, I want you to make sure you take good notes and complete the attendance quizzes. I'm seeing some pretty good responses to that, so hopefully that's helping you kind of understand the material a little bit better. And of course, if you have any questions, please don't hesitate to ask, and we can set up a Zoom session, and I can work with you more closely one-on-one. So looking at the calendar kind of going forward, we're going to revisit this, but this week is really pretty much dedicated to Chapter 16. And there's only going to be one CLO associated with that, which would be assessed on Monday the 13th. After that, we'll get into Chapter 17, which we expect to spend about 2 weeks. And then there might be some changes to the course as we kind of go forward from our original plans, depending on things that basically ongoing developments, especially considering the fact that we're all online now. So with that being said, let's talk a little bit about Chapter 16. So the name of Chapter 16 kind of implies what we're going to be working with, right? It's plane motion of rigid bodies, and now we're going to be looking at the forces and accelerations, right? So in the last chapter, we just looked at the kinematics. This one's starting to look at kinetics, right? What are the forces that are going to be acting on these bodies to cause motion? And so the chapter sections are pretty limited. There's not much in terms of the material for this chapter. That's why we're only going to be spending about a week on it. But the important statements are really, it's something we have to kind of make sure we cover. And the textbook shows pictures of these wind turbines here, and the idea is that the forces of the wind pushing on the turbine blades, okay, are causing the momentum exchange to go to the electric generator that's in there to generate electricity. And we can treat those fan blades or the fan itself as a rigid body and say, all right, well, how is it going to be spinning? So it's going to have some angular momentum, right? So the two sections we'll be discussing, the first off is going to be 16.1. That's kinetics of a rigid body. And keep in mind, this is plane motion. So this whole chapter is going to be focused on plane motion. So we're going to set up some general relationships, almost a review of previous chapters in which we started looking at rigid bodies, or really systems of particles. That's really kind of what we're treating. We're treating a system of particles, but all the particles are rigid with respect to each other. Then we'll take a look at some more applications using what we call constrained plane motion. So Chapter 16's objective, the CLO 10, is described as model rigid body kinetics undergoing translation, centroidal rotation, and general plane motion. That should cover both the sections that we're going to be covering in this chapter, and that's going to be assessed on the 13th. Okay, so make sure to keep track of that. So that's when we're going to be assessing it using the online Connect system. After that, to make some changes, we may have to add in a chapter or two that's kind of relying on the textbook, but I'll kind of communicate that as we kind of go along. All right, so the homework for Chapter 16 should be posted. First off, there's a reading assignment, and since we're still working on CLOs, and I imagine there's still a bit, you're going to probably be focusing on that today more than reading the new chapter, I've made the reading assignment due on Wednesday. Okay, and this is at 5 p.m. It shouldn't take too long. It's estimated at 18 minutes or so, but please be reading through the chapter while we're covering this material. It really helps to drive home these concepts. The homework assignment for Chapter 16 is going to be due on the Friday before its assessment, right? And there's quite a few problems because this represents one of the foundational concepts. This chapter in particular represents one of the major foundational concepts of dynamics. In fact, if you were to speak about dynamics, this is probably what people think about as kinetics of rigid bodies. It's kind of the grouping of all the material that we've talked about so far in such a way that we can analyze this to solve pretty complex problems. So I think there's quite a few homework problems because this chapter is so important. So please get started on this sooner than you have possibly your other homework problems, so you can get through them. And if you have any questions, I've already had a few students ask me questions. I will Zoom with you. I'll send you emails, whatever you need to do to get in touch with you to help you along in this process. The goal here is to help you understand the course material. So let's talk a little bit about or revisit some of the basic equations for motion of a rigid body and how we're going to apply those to this particular section. So beforehand, when we were talking about the translational forces, right? So forces of a group of particles, right? And we said, all right, we can consider the motion that there's a group of particles, any number, n particles, and if we were to sum up all the forces that are acting on each of those particles, it should equal the mass times acceleration through some center point, right? Some centroidal point. So this is coming from chapter 14. We're saying that the summation of forces, and this becomes a major equation here, the summation of forces are going to be equal to a mass times acceleration. It's a vector, but it's a bar, right? And remember, a bar represents acceleration of really, if you want to think of a point of the mass center G, right? So this is going to become helpful, and for the most part, we just said generalize, right? So remember, we had that example of a firework going off, and if we were to have the path of the particle, right? If the firework were not to explode, would be an arc, but if it did explode at a certain point in time, that explosion would occur, but the mass center would stay the same. Assuming that there's no other forces acting on it from wind or what have you. But that's just a re-representation of what we had seen from chapter 14. Now, if we also take this into account, we said, all right, let's define a new axis, or a new coordinate system. In this case, capital G, x prime, y prime, z prime. And what defines this reference frame is that it passes through the mass center. What we can do then is say, all right, well, let's take a look at the r vector from this, and remember we called that r vector r prime, that can represent any point or any little tiny piece of mass, right? And we said I, so we have many of those pieces of mass that go around that. And if you remember correctly from our work in chapter 14, we had said that the summation of moments about the centroidal point at that mass center G should be equal to the total angular momentum about G of the system with time rate, the time rate change of the angular momentum, right? So h dot, and this is a vector as well, right? So what we had really garnered from the previous section, and these two series of equations really state that the system of the external forces and moments is equipolant that's an important word, equipolant to the system consisting of a vector ma, right, centroidal mass acceleration, attached at G, and the couple of moment hg. Okay, so if we combine this mass acceleration and this rate of change of the angular momentum, we suggested that they should be equipolant, right? And if you remember, the definition of equipolant, as I described in class, is that the systems have the same resultant. Now, we had said that that's slightly different than equivalent, especially when it comes to a series of particles. Because those particles have no representation, there's no control between the particles. And so, while it's equipolant, it may not be necessarily equivalent. But what we're going to find for rigid bodies is that all of those particles are rigidly connected to each other in a rigid body. That's why we call it rigid, right? And so that's going to give us an interesting takeaway from this respect. And the way we can show this graphically is we'd say, all right, let's take a look at some potato, right, in space. And this is the last time we're really, this is still in 3 dimensions. Okay, even though the section really kind of describes it as plane motion, that's what we're going to be applying in general throughout the rest of this chapter. But in general, we'd say that the summation of forces is equal to the mass times acceleration, and then the summation of moments is equal to the rate of change of angular momentum. And so where does that leave us? So now we can start looking at problems. We say, all right, let's take a look at this radical dude here who's wakeboarding, and analyze all of the forces that are acting on this dude, and then say, all right, well, he has a mass center, right? So we'd say the weight's acting through this mass center, and all these forces are acting in different locations. So what we're going to see is a combination of the mass acceleration and as well as the rate of change of the angular momentum. And so that's how we're going to be analyzing the problems going forward here. So the next section starts to describe a little bit of how we interpret or how we work with angular momentum of a rigid body. So let's make some assumptions here. And the biggest one that we're going to be making is that the body itself is going to have a principal centroidal axis of inertia perpendicular to a reference plane. So what does that mean? We mean that this body has, at least in the motion that's associated with, it is the axis of rotation. So for instance, if this body is moving around its centroidal center of mass, or center of mass, and it's moving in some angular rotation, right, or omega here, that means that there is an axis of rotation that defines its symmetry. Because it has this centroidal axis of inertia perpendicular to the reference plane, that means it's symmetric about the reference plane. So there has to be a statement on the symmetry. Okay, so here, if we want to think about it, any of the results we get from this analysis are, so basically this is not valid for asymmetrical bodies or three-dimensional motion. We're going to extrapolate this a little bit if we get into chapter 18, but what we're generally saying is that this body does have an axis, a centroidal axis of inertia that's perpendicular, that's coming out of the page here. If we're saying that, then what we can do is we'd say, all right, let's take a look at every point. So if we're saying this body is rotating about this little point G, we're saying it's rotating about this little point G. If we wanted to find the angular momentum, right, the angular momentum as a vector around that point G, it's going to be equal to the summation. So we're going to add up all of the particles and the angular momentum of each of those particles. And remember, we had done this. This is a revisit from chapter 14. We said it's a summation from I equals 1 to however many particles n in our system. And it's the r prime I, and this is a vector, crossed with the vi prime, and then it's delta m I, right? So each mass there, the r cross v, or for the momentum of the particles, we'd see kind of going forward. And remember, this is representative of the motion of each of the individual particles with reference to that mass center G. Now what we can do here is we'd say, all right, let's replace the velocity here. If we're saying at this particular instance of time that it does have an angular velocity, omega. So we're kind of defining an omega that exists here, and we can replace the velocity and say this should be equal to summation of I equals 1 to n of the r prime I hat. I'm sorry, not I hat. I don't know why I put I hat here. It's just regular I, remember. Cross with, now we replace that velocity, which is just the omega cross r. So they have omega vector cross the r prime I, delta m I. All right. And so since we're working with general plane motion, we can now replace and say, well, let's look at these cross products. The cross products, as we have them defined, is that omega is always going to be remember, omega represents a vector. An angular velocity has a vector. It's a vector quantity. This vector quantity is always acting out of plane. And so the r vector will always be perpendicular to the omega vector, meaning we can just multiply the magnitudes here to get our relationship. And so what happens here is we can then pull the omega out of this, because omega we're saying is constant, or at this very particular instant, it's the same. So we say omega, and we pull that out, and we just sum up the rest of, now if we carried out that cross product, now it's just now this is a vector, omega is a vector, but the summation of I equals 1 to n is now just looking at the r prime I squareds multiplied by the little piece of mass there. And this is not a vector, right? So this right-hand side is not a vector term. And so what we're left with is that this representation coming from your statics class is just the moment of inertia for the area, and it's with respect to the centroidal axis. And so the way we write this is that this is equal to I bar omega. So if this is my angular momentum, if I then say, all right, well, let's take the derivative of this, that's equal to, well, the I bar is really a constant value, so we're just differentiating omega. That's omega dot. Remember, that's alpha. So this becomes I bar alpha. So now we have a relationship that says our h bar dot is now equal to this I bar alpha, which should be a restatement. Hopefully this is similar to what you've seen in your previous physics courses. And so what really we're saying here is that the summation of moments about some centroidal point G is just going to be directly equal to I bar alpha. And we'll kind of revisit that as we kind of go forward. But once again, and this is going to be asked on the attendance quiz, and this comes straight from the textbook. This text comes straight from the textbook. This is only valid for a symmetrical body that is not three-dimensional, that has a principal centroidal axis of inertia that's perpendicular to this reference plane. Right? So it's symmetric with respect to the reference plane. So now that we've got that taken care of, let's talk a little bit about plane motion of a rigid body. So the plane motion of a rigid body is, we're first generalize and say, let's take a look at a rigid body that has multiple forces that are acting on this part. If it's plane motion, we're only working in the x, y, and direction. So if we're looking at it from a scalar form, we have three equations to work with, generally speaking. We know that the summation of forces in the x direction should be equal to the mass times acceleration, a bar, in the x direction. The summation of forces in the y direction, that should be equal to mass times acceleration, a bar, y. And then if I say summation of moments about a centroidal point G, center of mass, that's equal to the I bar alpha. And these are not vector relationships because we are speaking about the dimensionality for these as we kind of are going forward. So we have a series of forces that are acting on this body, and then we say, all right, all those pieces there are kind of combined together, right? So what we're getting at is that if we have a rigid body, that means all the particles, right? So we'd say that originally the motion of a rigid body is completely defined by the resultant force and resultant moment about G acting on the body. This general statement is really what describes an equipolant system. But now that we're saying it's a rigid body, what we can make the general statement here, and this becomes very important. So this becomes very important. You should be taking these notes down. Is that for a rigid body under these kinetic principles, we have two systems of forces, I should say. Two systems of forces that are equipolant are also equivalent. Okay, so this statement here, which is it's a footnote in the textbook, but they bold it. Now what we can do is we can apply our series of equations to say now we have a resultant force and a moment. Those are equivalent to the inertial terms that are for the various particles that are formed on the body. Right? So now anytime that we had an equipolant system, they are also equivalent. Because we know the motion between the particles or the points in the rigid body are going to be kind of fixed. So how do we analyze this going forward? Right? First off, we have translation. So really, if we're just generalizing here and say that there's really no angular acceleration to the body, so now that the complete or if we're looking at the resulting force from all the external forces acting on the rigid body, this is just your summation of forces. It's just going to be equal to mass times acceleration through that centroid. Very basic, kind of just saying, all right, if we had no angular acceleration, this is what we would see. The next thing that we're going to add to that is say, let's take a look at rotation, but not just any type of rotation, centroidal rotation, right? So from here on forward, we're going to have the general case of translation, and we're going to say that when we have a rigid body that's with respect to this reference plane that's symmetric, right? It's going to rotate about a fixed axis that's perpendicular to the reference plane that's going to go pass through the mass center, right? And so this is where we get our summation of moments. So the summation of moments about G is equal to that I bar alpha. And so what we'll do is we're going to combine these two aspects to get the general plane motion, which is translation and rotation, centroidal rotation. We're going to combine those two to really say the mass moment of, let's say, the mass center G of a rigid body in plane motion moves as if the entire mass of the body were concentrated at that point, as if all external forces act on it. It's directly from the text, but that's our translation relationship. And then lastly, a rigid body in plane motion rotates about its mass center as if this point is or were fixed. And the point it's referring to is G. So now we have the mass center is going to be moving, much like a particle, for a translation, and the rigid body is the rigid body. In plane motion will rotate about this mass center. Okay, so these are the main takeaways for general plane motion. We're going to have a series of forces, right? And if those series of forces don't all act, the resultant of those does not act through the mass center, we're going to have some rotation. And that rotation is going to be defined by the I bar alpha. Once again, if it's symmetric, about the reference plane. One brief motion or mention in the textbook is this principle of transmissibility, and this is coming back from chapter 3. And what that was telling us, for especially when looking at rigid bodies and analyzing the forces that are acting about rigid bodies, is that if we were to have two forces, right, F and F prime, and these were to have the same magnitudes and direction and line of action, but they're just at different locations on the rigid body. That means that if I were to take the moment about any point, right, so if I were to take a moment about here, on both of these bodies, the R cross S are going to be the same. If the way you can think about it is that the perpendicular distance between any point is going to be the same, that means the moment's going to be the same about those points. So we had said that they're therefore equipolant, right? These two, this would be equipolant. But as we had said for plane motion of a rigid body, that equipolant here is equivalent. So when you're analyzing these problems, these forces are the principle of transmissibility, whereas before it was just an axiom, right, that you kind of just take for granted. Here it shows that, or defined at, for a rigid body, that this holds true. So if we're going to be working with problems about motion of a rigid body, how do we analyze these types of problems? Well, pretty straightforward is you're going to be using free body diagrams, right? So a series of free body diagrams that are going to kind of build up and represent all of the bodies that you're planning to analyze. And so what has this done? So typically the free body diagram goes through the same process that you all have done before. And then also, we're going to have that kinetic diagram. So it's going to be the equivalent systems, right? Remember we had said that summation of forces is equal to mass times acceleration, right? And then summation of moments is going to be equal to the I bar alpha. But that's summation of moments about a singular point G. So how do we analyze these points kind of going forward? Well, I'd first isolate that body. So that's the number one thing that we have to do whenever creating a free body diagram and doing this kind of these dynamic analysis. So for instance, if I have this bar and it has a mass m, and say for instance we know that, okay, that means that the weight of this body would just be equal to mg. So if we know the mass of the bar and it's rotating and it has some external forces or external moments that are applied to it, and it's there's a pin connection here at P, and we say, all right, it's being acted upon by this external moment, we have to create a free body diagram. So I'd redraw that body. Okay. So here's the body here. And we say, all right, well now let's analyze all the forces that are acting on it. And so if we have a pin connection at location P, and we have the centroid given to us at the center here at G, we'd say the forces then for a pin connection are going to be X and Y axes. So here we can generalize and say, all right, well, we don't know, so we're going to have some force in the Y. So we'll say capital P, Y direction. We're going to have some force in the X. We don't know the direction of this. We'll just say PX. We know there's an applied moment. So you need to make sure you put all applied forces and moments. So we know there's an applied moment probably around that point P. And then we know that there's the weight of the body, W. And so all the forces that we represent, the big ones here, right? So we have the applied forces, and moments. In this particular problem, it's only the moment. And then we have the support forces and moments as well. Because we could have a fixed connection, so there might be a fixed moment that's applied. And so for the free body diagram, you have to consider those, and then also what we call the body forces. Now here, most generally, that's going to be just the gravity. And so if we were looking at this and we're going to analyze this distance here, remember, this distance here would be L divided by 2. We'd also want to put some sort of coordinate system, and here I'm okay with, and the book shows this as well, is to kind of generally define it, right? So we don't have to necessarily put it at any one particular point, because remember, we can analyze this or move this point around for whatever we're looking for. Here, x and y is considered positive. And another thing the book shows is that we can assume that the moment here is going to work with the same vector relationship, right? So this would be a positive moment, which would be the counterclockwise rotation. So if you're using right-hand rule, your thumb would be coming out of the page. So these are the forces acting on the body, and now we can use our red equal signs, because we know it's equipolant and equivalent. And so if I take this whole thing here, let me delete everything else except the body. Okay, so now we could say this is equivalent to our kinetic diagram. And so how do we manage our kinetic diagram? Remember, this is the mass and acceleration terms for the description. Now, here we can generalize and say, let's go in the positive direction. So we say that the mass times acceleration, a bar, and this is going to be in the y direction. We'd say this is mass times acceleration, a bar, in the x direction. And we're also saying that there is a centroidal I bar multiplied by its angular acceleration. That's applied at that center G. And so that's where you make those applications for the mass centers and the locations in the area. And if I were to be applying this, right, you would then say, you can come and say that the summation, if I were to be solving through this problem, I'd be saying that the summation of forces in the x direction are going to be equal to the mass times acceleration in the x. The summation of forces in the y direction equal to mass times acceleration in the y. And then the summation of moments about the point G is going to be equal to I bar alpha. But what if we were to want to do summation of moment that's about some other point? In this case, what if I want to do summation of moments about location P here? Well, I can do that as well, but I have to make some modifications, right? This summation of moments only works well if you're working in the center of the gravity there. If you're doing about some other point, the way we can generalize this is say that the summation of moments about some point P is going to be equal to the I bar alpha, right? Which, remember, I bar is typically given as a geometric value or be given on a problem or something you have to look up with reference to the textbook. I'll do that over here. I accidentally moved my bottom of the eye here. But we also have to add in the fact that we changed position, okay? And so the way that we do this is we say we add in, now, if we know the mass of the system multiplied by its acceleration, and then to take the perpendicular distance d. And so the way the book draws that is perpendicular distance there. And so what does that give us? Well, that's going to give us the angular momentum, right? The time rate change of angular momentum for the mass center. This one we know we acts through the entire body, so that's always going to be there. But anytime we take a mass or summation of mass at any point here, we also have to consider the fact that the main or the center of mass is moving with a certain acceleration. The way we can define that is we say the mass times a bar and the perpendicular distance, that's equal to whatever the r vector coming from the mass center, in this case g, going to the mass center g with respect to the whatever point you're trying to do your summation of moments, cross with the mass times acceleration vector here. So this is a vector relationship since it's a cross product. And so that is equal to this perpendicular distance only in the case that if the acceleration is in line with that relationship here. So you have to remember this general relationship is kind of an addendum to say, okay, if I want to apply summation of moments about any other point, I have to make sure that I take that into account. Right? So the last part of their last section or portion of the class describes applying this to systems of rigid bodies. And so the very last statement I'm going to make about the material for this chapter is that we can say, all right, let's now take a look and say, well, we can consider, say for instance, if I'm looking at this this forklift as a single body and all the forces that are acting on this, and then I were to consider the mass that it's carrying as another body. Well, I can combine those two through those relationships of the forces that are in between, or I can consider them as two parts or a system of rigid bodies. So how do we treat those? Very simply stating is that we can say the summation of forces, right, should be equal to the summation of mi. So for all the bodies that you're working with, multiplied by a bar I for each of the bodies. Same thing goes, you can do the summation of moments about any point P should be equal to the H bar dot, the H dot G, or of any point not G, but P itself. And then we'd say, all right, if we're looking at any point for our angular, the derivative of the angular momentum here, that's going to be equal to the summation of I bar alpha in each of the terms in series. And then we add in the summation of mi a bar I in the perpendicular distance I. Or we can say it from a vector standpoint, summation of I bar I alpha I, these are vectors, plus the summation of the R from the basically going to the centroid or the center of mass from that position P, I cross with mi acceleration a bar I. So we can apply these to any series of rigid bodies or systems of rigid bodies. So if you have multiple rigid bodies, you can analyze these separately. But ultimately, the main thing here is that if we're working with a single body, right, or if we're only working in really just plane motion, we can only really solve for three unknowns. Okay, so for each body that we have applied to this, we can then solve. If we can solve for more unknowns here. But remember, keep in mind that they also have interaction forces. So sometimes that doesn't always help us out. Okay. Right. So with that in mind, what I'm going to do is, since it's already at 40 minutes and we don't have time to go through an analysis, what I'm going to do is I'm going to separate it here. So this is the class portion, and so you have to make sure to cover this on Monday. And on Wednesday, what we'll do is we're going to work out some example problems. Since this took a little bit longer to discuss, this is a very important section, so I'd like to dedicate a whole class video on just working example problems for this section. And so that